Muhammad Wahyu Setiamukti. Apa nih cewek nih? Nggak bisa. Nggak besar gitu manjat.
you have the headphones. No, but here, should I mute?
Good afternoon, distinguished guests, students, and esteemed faculty members. Welcome to the 12th IEEE COMNETSAT 2023 keynote session. I am Cynthia from Institute of Technology Telkom Purwokerto's Software Engineering major, your MCs for today's event. We are thrilled to have you all here with us virtually as we delve into the fascinating realms of networking, data mining, machine learning, and research. Before we dive into the exciting keynote sessions, let me take a moment to acknowledge our event's organizers and sponsors. This event is proudly organized by the IEEE Communication Society Indonesia chapter, Indonesia section IEEE Aerospace and Electronic Systems Society, Geoscience and Remote Sensing Society chapter, and Institute of Technology Telkom Purwokerto. We also extend our gratitude to the technical sponsorship provided by the IEEE Indonesia section. Special thanks to our co-hosts, Institut Teknologi Telkom Surabaya, Institut Teknologi Nasional Malang, dan Politeknik Negeri Malang. We are honored to have COMNETSAT and KEYNOTE as our event patrons. Before we start with the event, kami menghimbau kepada seluruh peserta untuk men-rename nama Zoom-nya menjadi nama institusi _ nama lengkap. Now, without further ado, let's officially commence our event by calling upon Director of Institute of Technology Telkom Purwokerto, Dr. Tenia Wahyunirum SCOM MP, to deliver the opening speech. Kepada Ibu Tenia, waktu dan layar dipersilakan.
Oke, terima kasih, Cynthia. Very good afternoon, ladies and gentlemen. Assalamualaikum warahmatullahi wabarakatuh. The Honorable Professor Suyu from University of Technology Sydney, the Honorable Professor Liliana Strakovic from Simon Fraser University, Canada, the Honorable Mr. Aulia Burhanuddin, Dean of Faculty of Informatics, and all participants today. On behalf of the Institute of Technology Telkom Purwokerto and Organizing Committee, I warmly welcome you to the 12th IEEE COMNETSAT to the 2023 keynote session. In this session, the speakers will give us insight into the importance of data mining and machine learning for analysis of network traffic, and also how to do a good research. In this session, the speakers will give us insight into the importance of data mining and encourage innovation and progress in various fields, from technology to art, and is the key to scientific and social progress. We hope you will get benefits and new insight from this event. Thank you and enjoy this event. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you, Dr. Tenia, for setting the stage for what promises to be an enlightening event. Now, let's move on to our first keynote session, data mining and machine learning for analysis of network traffic. Today, we are privileged to have Prof. Liliana Strakovic as our keynote speaker. This session will be expertly moderated by Mr. Mega Pranata Inkom. Kepada Bapak Mega Pranata, waktu dan tempat dan layar saya persilakan.
Okay, thank you very much for Cynthia Tio. Good afternoon, everybody. The Honorable Rector of Institute Teknologi Telkom Purwokerto and the Honorable of Professor Liliana Strakovic, and also all the participants. Okay, welcome to the keynote session of IEEE COMNETSAT 2023. In this session, we will talk about the machine learning for detecting internet traffic anomalies, and the speakers will be Professor Liliana Strakovic. Before we move to the main session 1, I will read about Professor Liliana Strakovic. Professor Liliana Strakovic, currently a professor in School of Engineering Science, Simon Fraser University, Burnaby, British Columbia, Canada. Her research interests including communication network and dynamical system. She served as IEEE Division Ex-Delegated Director, President of the IEEE System, Man and Cybernetics Society, and the President of the IEEE Circuit and System Society. Professor Trajovic serves as editor-in-chief of the IEEE transaction on human-machine system and associate editor-in-chief of the IEEE Open Journal System Engineering. She served as a distinguished lecturer of the IEEE Circuit and System Society and a distinguished lecturer of the IEEE System and Cybernetics Society. She is a fellow of the IEEE. Okay. For the first session, it's Professor Liliana.
Thank you very much. Thank you for the introduction. I'm going to start sharing the screen, and I hope you can all see my slides.
Okay, it's good. Professor, I'm sorry. We have 1 hour for your presentation, and after that, we will follow with question and answer session about 15 minutes. Thank you very much, and time and screen is yours.
Yeah, thank you very much. What did you say, 1 hour or 45 minutes?
1 hour for presentation and 15 minutes for the question and answer session.
Thank you. So I'll speak slowly. So thank you very much for inviting me, and thank you very much for giving me opportunity to talk to your students. I understand it's for both IITP and from ITN. And so I learned about universities in the acronyms. So I'm very pleased that I have opportunity to talk to students, and I understand these are undergraduate students and lecturers. So I'm going to try to speak slowly, and I'm going to try to talk in general about the research that I have been doing with my graduate students and sometimes even undergraduate students who visited my lab. At Simon Fraser University, I have a communication networks laboratory. I had it for the last 25 years since I came to SFU in 1998. And I also put a URL there because we put a lot of talks and a lot of papers and a lot of software tools. So there is a variety of information that is publicly available. Because I usually say that I'm paid by taxpayers' money, so everything what I do is publicly available. So you don't need a password in order to download whatever we do. And I come from School of Engineering Science in Simon Fraser University. Actually, we are located in a suburb of Vancouver. It's called Burnaby, of course, in British Columbia, Canada. And I thought I'll show you a beautiful photo of our campus on a sunny day. Unfortunately, we do not have many sunny days. So this is unique, but on a sunny day is really one of the most beautiful places in the world. So when I come to places like Indonesia, and this is my first visit here, I'm delighted to have so much sunshine because in Vancouver, we all miss sunshine. So this is our main campus. It's called Burnaby campus. It is on Burnaby Mountain, and you can actually, we have a nice view of Indian Arm, right? And Pacific Ocean is here. And Vancouver is on the upper left side. We also have additional campuses. One is in Vancouver, mainly business. And we also have a campus in Surrey, that's across the Fraser River, our mechatronics department there. And we have a new school for sustainable energy. But the main campus, it's a Burnaby campus, and this is where the School of Engineering Science is. We call it School of Engineering Science, even though it is really electrical engineering. And for political reasons, when in 1965, the university was formed, University of Victoria got a department for electrical engineering, and we became a School of Engineering Science. And you see that we celebrated, we were formed in 1965, and this is a logo from 2015 when we celebrated 50 years of the university. So we are a relatively small young university in Canada. So this is the outline of my talk. So I'd like to introduce the topic. Why is traffic collection that important? And especially these days, it's possible to do analysis of data that other people collect. Because in research community now, the data has been made available to the researchers. You don't have to buy your own equipment. You don't have to have connections with the telecom operators to let you. People are interested to actually apply some machine learning algorithms as we did in order to analyze the data. So I'll talk about traffic collection, characterization, and modeling that has been around for a long time. Even in the beginning of 20th century, when the first telephone networks were put in place, the telephone companies actually did the traffic collection and did characterization of the traffic and did the models at the time when communication networks only carried voice. It's just they didn't share data with anybody else. It was basically done within companies. I'm going to mention 3 case studies that we were involved in. British Columbia Network, BCNet. It's a local network that provides services to universities, hospitals, and research institutions in what we call Lower Mainland British Columbia, because British Columbia, it's relatively large, and what we call Lower Mainland is this belt, the area very close to the US border. We also had a collaboration with the ECOM. It's a public service. They actually support 911 calls, emergency calls, and we were fortunate to have a collaboration with one of the ex-students who became a manager. So we were able to get hands on the data from ECOM network. This is a radio network, so it's old-fashioned technology, but it was interesting to study how people use that ECOM network. It's not a public network. This is only used by police, fire departments, and emergencies. Then I had a collaboration with people in China, because one of my students actually came from a company in China, and he had connections in a network operations center north of Beijing. So we collected data from ChinaSat. It's a service. So it's very interesting to start studying how people use the internet. And finally, most of my talk and most of my research these days, it's really dealing with internet, because it's such a rich source of information. And we'll talk about machine learning models, a variety, experimental procedure, and I will also talk about performance evaluation and some conclusion references in case you are interested in the topic. Sorry. So traffic collection, characterization, and modeling, important topic, especially these days, when the network carries not only voice, but also carries data, video, images, all sorts of social interactions. So traffic is much richer than what we had seen before when the network only carried the voice. So at that time, it was well accepted that the traffic created by voice was easily modeled using Poisson models, very tractable. So queuing theory was introduced, so one could have closed form solutions in terms of queuing time, workload. But with the onset of the internet use as part of our daily life, we realized that traffic is now very different. So the collection and characterization modeling of traffic became quite an interesting research topic. So traffic measures help us understand characteristics of network traffic. They are basis for developing traffic models, and they're used to evaluate performance of protocols and applications. Why do we want to develop traffic models? If you want to simulate any new application, any new protocol, you would like to simulate it with realistic traffic. And so either these simulations are trace-driven, when you collect the traffic and you drive your simulation using a trace, or you create a model based on the collected traffic. And sometimes people also created synthetic traffic models. So models are important in order to evaluate performance of various protocols. Because they would like to understand the customer base, how is the network used. You probably realize the network is used differently during the weekdays. It's during weekends. In summer and winter. So understanding from a business point of view. Traffic prediction is more difficult, but it's also important in order to figure out what are the future capacity requirements. Because one to plan future network developments. So now the collected traffic from networks are used to evaluate the internet topology. And more recently, what was of my interest with my graduate students is to classify traffic and network anomalies. And as I mentioned, it's not only grad students. Very often I have undergrads, because we do have the action item to actually involve undergraduate students in research as early as possible. So for example, I participate in a so-called MyTex program, where we get students for 12 weeks of the summer from various institutions in order to come to Canada and participate in research. So usually I get students from IITs in India, from Brazil. So if you do not know about that, I suggest that you check for MyTex, and you can always send me email and be asked about that. Just to tell you, it's not only grad students, it's very often undergrads who actually participate in these projects. So for a while, we worked on understanding internet topology, and we tried to figure out, as internet grows, can we find some elements, some identification that actually there are some parameters that don't change. And it turns out that if you are interested in graph theory, you can look at the graph, static graph of the internet, and you can figure out that certain things have not changed, even though the internet grows as I speak. And more recently, and this is probably a major part of my talk, a few, especially from 20 years ago, when these worms and viruses took internet down for a prolonged period of time. It doesn't happen today anymore because the system administrators know how to prevent it, but ransomware attacks are still a reality. And you have probably heard news that sometimes the companies and universities have the data encrypted, and the data is decrypted only when the ransom is paid, which means the universities and companies have to pay the money to the malicious attacks. So now I'll mention something about how do we model the traffic, and it might be too mathematical for you, but self-similarity means fractal behavior. So this was a novelty that was discovered in mid-90s, that is traffic that's collected from the backbone of a company where I had to work called Bell Communications Research. That backbone connected the university to the rest of the internet. So the research were collecting the traffic, literally shoeboxes of traffic were collected. And so they tried to analyze and realize, wow, so model. So they found out that the traffic that's these days carried over the internet, as I mentioned, it's voice and video and images and all sorts of interactions that we have, is actually fractal in nature. Mathematically, we call it self-similar. So there is a very strict definition about self-similarity by looking at the autocorrelation functions. And if this is above your head, you don't really have to remember. Just keep in mind that the traffic is basically fractal in nature. And to sort of illustrate what it means, I'm going to show you a traffic trace. It's from an MPEG traffic trace of a movie. And the idea is taken from this seminal paper by Walter Willinger and his team. And it was published in 1994. And it was a major seminal discovery that actually traffic is fractal in nature. So if you look at different time units that we see, and I collect, let's say, 4 frames of this movie, the coding scheme was such that each frame lasted 40 milliseconds. That means 4 frames is 160 milliseconds. And I plot how many bits do I get in a movie scene collected over 4 frames. And so we change the time scale. And let me take 16 frames and collect the number of bits per 16 frames. Of course, the vertical axis is going to change because every line now represents how many bits I have in 16 frames. Whatever you see yellow on the left-hand side, it's this now little yellow in the middle, but I still see qualitatively the same behavior, peaks and valleys. I can do this many times. And so this is basically an illustration that this traffic that was collected from this movie, I think it was a Star Wars, because it was very popular at that time, it's actually fractal in nature. That means you zoom in, you zoom out, you still see the qualitatively the same behavior. And just to show you that that's not the case if you model your traffic using Poisson model, right? We do the same. This is a Poisson model of a traffic. You can actually on one scale use a Poisson model, but you cannot use that model on different time scales because you see a big difference. When, for example, I go to the time scale of 64 frames, I basically get a noise. So this is an illustrative way to show you that actually, even if you can capture properties of the traffic on one time scale, you cannot use that model on different time scales. And something about internet topology that was important discovery. It was done by Brother Falutzas and the collaborator. The paper was published in a journal in 2003, but the discovery was made around 1999. We can actually look at the static graph of the internet by looking at autonomous systems. For example, IITP, it's only one node. It's one autonomous system in the internet. ITN is another autonomous system. And every autonomous system is well defined and it has AS number, but one can look at the graph of these autonomous systems and actually find out that these graphs have very interesting properties. These are not completely connected graphs. They are not random graphs. They are what we call scale-free graphs. These are two major discoveries in the mid-90s and late 90s that made us better understand the traffic that is carried by internet, and also how is the internet connected, at least on the autonomous system level. So you might imagine that one of these nodes, it's actually a network of networks within your campus, ITN or ITTP, you do have many computers inside. So each of these nodes is actually a network of networks. And then you can also add the dynamics. These are not static networks, but that gets a little bit too complicated. But you can add dynamical models of protocols, and you can attach this dynamical model to a node, but that's usually quite difficult task. But that's why I'm interested in dynamical systems. So two important things, understanding traffic and understanding how the topology looks like. So if you are simulating a network, keep in mind that the traffic should qualitatively resemble fractal behavior, and the topology should resemble the scale-free graphs. And there are actually some tools. So like Bright was one of the tools. I don't know if it's supported anymore. You can say, give me a network of 500 nodes, and I would like the network to have this scale-free graphs property, and they're going to give you a network that you can use in order to do simulations. Now, I was involved in a couple of case studies, and probably I'm just in general going to tell you one was BCNet. It's a local advanced communication network in British Columbia, and we were fortunate to actually get a grant, and we bought a device. We paid quite a bit of money, maybe $60,000 for a device that would actually be able to collect the packets going from BCNet to the customers. And so this is how the device looked like. It's a packet capture. You can see that BCNet has three transit providers, right? Transit provider 1 and transit provider 3 and transit provider 2. I cannot give you the names for proprietary reasons, but these are major companies and universities. And we actually connected the device. The company called it Ninja Box. It's a data capturing device. And it's really collecting a piece of the optical signal. And based on that piece of the optical signal, we could collect like the IP addresses, the timestamp, so we could actually be able to figure out the traffic model. It's really a statistical process. You basically collect when the packet arrives and how many bits are per packet. These are some gory details about the hardware. You can't really do a collection like this with software. We are talking about 10 gigabits per second lines. We also had two boxes, one for 1 gigabit per second line. So you have to do this using hardware. And so there are companies who specialize in building hardware boxes in order to be able to collect data. Of course, there are all sorts of proprietary issues. You need a permission for that. But we were fortunate to have a collaboration with BCNet at that time. Another case study was ECOM network. It's not a public network. It's a network that was used by police. And it's a it's an emergency preparedness network. It's an old-fashioned technology. It's a trunk radio system. It enables both voice and data transmission, but voice accounts for 99% of the traffic. More than 85% of the calls are group calls. That means if there is an accident, a police would go to the accident, and maybe 4 or 5 policemen, personnel, and they would use these push-to-talk devices in order to talk. And so we were collecting the data to understand how people use these legacy systems, especially because ECOM was very interested to get a model in order to predict how many channels do they have to put in order to keep up with the increasing demand. And each channel is very expensive. At that time, it was like 100K. So this is why they were interested in the traffic model. And so now this is how it looks like. This is ECOM network. You can see Burnaby is where my university is. And if I was giving this talk from my university, I would be sitting there. But I'm very pleased that I'm not there, but I'm here. And you can see how the structure looks like. And you can see that these are police, fire, and ambulances. So a very specialized network. And if you're interested, we did have at that time a journal paper that showed quite a bit of interest because it's such an unusual network and a rare collection of data. As I mentioned, we also studied CHINASAT. It's a direct PC system. And so this uses the geosynchronous satellite. It was deployed by Hughes Network Systems. It has various television services. Its transmission rates are quite limited, but was just very interested. It was a hybrid network, satellite and terrestrial network. So there are some tricks that I used in order to use both terrestrial and satellite network. So we were very much interested in tricks like TCP splitting and spoofing, if you are into TCP. And I hope you know that it's a transport control protocol. It's a protocol that actually carries most of the things that we see on the internet. There is another protocol called UDP, and it's used also for video. But majority of the traffic that we see to the internet is carried over TCP. This is the structure of the network, and I'm showing you just, if you get into this, it's very important to understand the network. So you have to understand where the data comes from. And so you can see this is a satellite user in internet cafe in one of the Chinese provinces. There is a modem. There is a dial-up internet service provider. There is a network operations center. In this case, it was located north of Beijing, and we were fortunate to get actually a huge amount of data from them. Then the request code was to the internet, and whatever is requested comes down to a satellite to the user, because the request is usually a simple message. Send me a URL, send me the video, and the video comes down. So that's a structure of the network, right? So that's a little bit about collections that at least I was involved in. More recently, we actually look at the data that's publicly available, and we are looking at the computer worms and viruses, electrical failures, ransomware attacks, and one can also look into IP prefix hijacks, misconfigurations. Some of those things are really not malicious. Some of these things happen because, for example, a traffic station fails. But that reflects on the connectivity of internet. And if you look at the traffic trace, you can actually see the effect of these traffic failures. For historical reasons, we looked at 3 major events. These are worms and viruses, Slammer, Nimda, and Code Red 1. We also looked at electrical failures, such as Moscow blackout and Pakistan power outage. And we also looked at the ransomware attacks, especially recently, because we were interested to see, can our tools actually help figure out whether there is an attack or not? We looked at VanaCrypt in 2017, and more recently, Vestrock attack. Vestrock is a company. It was attacked by malicious users, and it was a ransomware, and it took companies' operations down for a prolonged period of time, and it happened in January of 2021. Why are we looking at more recent data? Because internet has changed, protocols have changed, users have changed. So it's very important to actually keep up with time in order to capture what's currently happening with the system. We are looking at the anomalies that are, we call the BGP anomalies. Border Gateway Protocol is the factor routing standard that anything that goes through the internet goes through BGP. And as I mentioned, these are the collection sites that we did. And we looked at the two sites, RIPE and route views. RIPE collection sites are usually not in Europe. And route views is a project from University of Oregon. So the collection sites usually North America, even though they're spread. So you can actually find them worldwide. Visualization is quite important. So before we embark on actually applying machine learning algorithms, we would also look to find out what are we trying to analyze. So for example, this is a Pakistan power outage capture from January 2021. What you see on the graph on this axis is a date. So it happened from January 7th to January 11th. It's a period of time that we are interested in, right? So there is 1 day of, maybe it's even less of a day when the power went down. On the vertical axis, we have number of implicit withdrawals and number of announced prefixes. These are features from the border gateway protocol messages that we collected. And so we look at the RIPE, for example, on the left, route views on the right. They both collect data from the same internet, but we were always interested to find out whether there is a difference between two collection sites. But keep in mind, they're collecting the data from the same network. Notice that we talk about number of implicit withdrawals and number of announcements. These are what we call volume features. And usually if something bad is happening, especially denial of service attacks, it's the volume that's going to be affected, the number of packets that are going to be transmitted. This is a Western ransomware attack. You see it's a prolonged period of time. And it turns out that algorithms don't really work very well for this kind of phenomena. And I'm going to show you some of the results. Again, number of announced prefixes, number of implicit withdrawals, and the date. And this happened in January of 2021. And as I mentioned, Westrock is a big company in US worldwide, and they were very much affected by the ransom that they eventually had to pay. People usually don't talk about it, but the operation of the company was off for a prolonged period of time. Notice that we look at the window when the ransomware was reported. How do we know? From white papers, from email messages, from announcements. And we also look at the time before and the time after, because if you have done any work with machine learning and data analysis, you would like to have a balanced data sets so that you can actually train the model and test the model. So the blue dots are all regular points outside of the window that was reported, and the red is within a window. So just to give you some feel about that, the collection from 2001 and 2003 was actually rather small. You can do this kind of analysis on a PC. You don't need a CPU. You don't need a GPU. You can see we are really not talking about huge data sets. So these are three well-known viruses called Red, Nimda, and Slammer. Route views started the collection only in 2003. So we don't have a collection from 2001. So just to give you a feel that we talk about 6,600 minutes of regular data, 600 minutes of anomaly data. We're also splitting this into training and test. Usually in engineering problems, you would take 80% of the data for training and 20% for test. But we also experimented with different division. So for our problems, 60-40 produce better results. So we take 60% of the anomalous data for training and 40% of anomalous data for test. We've done all sorts of experiments. Information about blackouts and outages. We looked at Moscow blackout, very short event. It only lasted 4 hours in May of 2005, but it propagated the internet. It propagated the internet. You could actually see it, right? And we always look at the RIPE and routes, okay? Again, quite manageable data set. Ransomware attacks, prolonged period of time. And so you can see we talk, for example, here about 8 days, right? And in terms of minutes is a larger data set. So now about machine learning models, and I'm aware of time. So of course, we played with a variety of models. And usually it's a nice exercise, especially when I get students who come to visit me for 12 weeks over summer, and these are undergraduate students, usually third-year students. I would give them one algorithm to play with. And of course, I have my grad students who are going to guide them and help them. But by the end of this 12th period, they usually know what the algorithms are, and maybe even be able to play with some of the parameters. So we look at deep learning. These are multi-layer recurrent networks. We look at something new, broad learning systems, and gradient boosting decision trees. So network intrusion detection systems use diverse deep learning algorithms, and some of the systems are already deployed. We look at the convolutional neural networks, recurrent neural networks, deep belief networks, autoencoders, and more recently, boosting algorithms. We are very interested in fast algorithms because we would like the system administrators to be alerted if something bad is happening, to take the network element down so that the virus doesn't propagate, right? And so this is why it's important to have fast algorithms. So we were interested in gradient boosting decision trees because they are relatively fast. All of these algorithms are what we call supervised learning. That means the data points have to be labeled. So the labeling process is very time consuming. And so the future of the algorithms is really to use semi-supervised or unsupervised learning, when the algorithm learns without having the labels. But it started all with a very traditional support vector machine, SVM, then long short-term memory, and its bidirectional version, simpler version of LSTM, which is GRU, and its bidirectional version, and then a family, what we call gradient boosting decision trees. And there are quite a few of them. They were introduced approximately in 2018. So we looked at XGBoost, LightGBM card boost, and around the same time, broad learning systems that were a departure from deep learning. And so I will show you the architecture. They're also much faster than SVM, LSTM, and GRU. This is a high-level view of convolutional neural network. So the high-level structure, we have input layer on the left-hand side. And this is to remind us that our data are really time series data. So these are not images. These are not two-dimensional systems. So we work with the time series data. So it's input layer, it's one-dimensional. Then we do convolution, feature maps, max pooling, convolution, feature maps, then flattening. And on the right-hand side, you see fully connected layers, not too many, and finally the output layer. In our case, the output layer are two nodes. Either the point is declared as an anomalous point, or it's declared as a regular point. One can do more complicated things and say, well, I'm not only interested in whether it's anomaly or not. I'm interested in what kind of anomaly it is, and one can do that. It's more difficult to identify which of the viruses it is, so you might have more than two nodes. But whatever results I'm going to show you are really what we call a binary decision, right? Whether the point is so the output layer only has two nodes. This is a deep learning network. You see, we really don't need to use many layers. I know in image processing, sometimes people use thousands of layers. For us, it was enough to have 37 RNNs or 109 RNNs if you use another data set. I'm going to mention this also. And 80 fully connected layers on the first layer, 32 in the second, and 16 for the third. So it's very manageable network. Whatever I talked to you about until now was about border gateway protocol. But there are also other data sets that we studied. And in this slide, I also mentioned NSL-KDD. It's an old data set, very popular in image processing community. Now it was cleaned up and it was republished by University of New Brunswick. It has also data set from networks. And we also applied the algorithm to see how are the algorithms going to work with this NSL-KDD data set. This is a high-level view of one of the cells for long short-term memory, or LSTM. It was introduced around 1998. Then it was almost forgotten. And then when people realized, you know, we have hardware facilities, we have good CPUs, we have GPUs, we can actually run this with thousands of layers, it became more popular. So LSTM is one of the classical cells that are used in neural networks. You can see the input, the output, inside structure, right? And so these LSTM cells are stacked. There is input layer and the output layer. And behind this is a nice mathematical theory. And as usually mentioned, it's always interesting to study math because we don't want to really learn by trial and error, because it's very difficult to learn anything by trial and error. So it's much better to understand why these algorithms converge. What is the region of convergence? Is there any fixed point? How do I choose parameters in order to hope that the algorithms converge? So usually I advise my students not to do too much trial and error, but better to spend time understanding, right, why certain parameters actually help the algorithm converge. This is a simpler version of LSTM. It's called gated recurrent unit, or GRU. Similar idea, just a simpler cell, but they are equally powerful, equally good. They take less time than LSTM because it's less of the processing that has to be done within a cell. Broad learning system is something very interesting, very different from deep learning. And instead of making your network deep, you can make your network flat. So you can see all these nodes, they're flat. There is only an input layer and the output layer, and just one layer in between, but there are many, many nodes in this layer in between. Two groups of nodes, map features and enhancement nodes. And this is a contribution from Philippe Chen and his group. At that time, he was at University of Macau. Now he moved to South China University of Technology in Guangzhou. And he was credited with a new architecture. And it turns out that it's very fast architecture and very interesting because it has this, what we call incremental flavor. That means if I'm not happy with the performance, I can add nodes, both map nodes and enhancement nodes. There is, of course, mathematical theory behind. Not only that I can add nodes, but I can also more you can data and exploit this incremental property of this network. Why these networks fast? Because they don't use what we call backpropagation, which is typical for LSTM, GRU. They use what we call pseudo-inverse. So more, it's a mathematical expression for managing the matrices. And so that makes them very fast. If one wishes, one can add depth. In BLS, we call the depth cascades. So you can cascade the map features, or you can cascade enhancement nodes, or you can cascade both. You can also add incremental flavor for the nodes and for the input. So if needed, you can add the depth. In our case, the depth helped, but we didn't really work the more than 30 to 40 of cascades, unlike in image processing. And if you are interested, if you look at the papers that use BLS for image processing, they would use thousands of these cascades. In our case, that was not necessary. Our own contribution was to add the features. And so this is a structure when we actually have a feature selection algorithm up front, because we find out that understanding the features is very important. And by selecting high-ranked features and selecting features that are actually going to help cluster the data in such a way that the algorithm would work better really helps. So this is, we call it VFBLS. F stands for features. So the research community always has some new algorithms to experiment with. We were very much interested in the speed, and it turns out that GBTD algorithms are very fast, especially the GBM. And so it depends on the application that you want to do. In our case, speed was very important. So a little bit about experimental procedure. We built software, and we make the software publicly available. So this is our latest view of architecture that we call cyber defense. So you can see we have a data container with data. Data can be custom data sets. or it can be a collection of data. So up till now, I was telling you about the data collected from ripe and outfields, but one can have a custom data set, for example, an NSL KDD, or I'll mention later there are a lot of data from a Canadian Institute for Cybersecurity, huge amount of data from a very controlled environment, from testbeds. So one can really have a data container with a variety of data sets. There are two paths, real-time and offline. In real-time, we can have a real-time data retrieval, then we can do feature extraction, and then we can move to data processing. If we do this offline, we do offline data download, we can do feature extraction. Something that I didn't mention is when we extract these features, such as number of announcements, number of withdrawals, variety. In BGP, we have 37 of these features. We can also do something called label refinement. So even though, for simplicity, at the beginning, we thought everything what was reported is anomaly. That's really not true. Because during the time of anomaly, we also had regular users. And the actions of these regular users were also captured in the traffic. And so in order to do better, we did what we call label refinement. That means I'm going to look at the window of anomaly, a virus, or ransomware attack, or power outage, and I'm going to try to extract the points that are actually regular points. And we were hoping that this is going to do better for our algorithm performance. Sometimes it does better. We use two algorithms for that. One is K-means. I don't know if you had courses in statistics. K-means, it's a very classical approach, clustering approach. And we also use iForest, which is a little bit more current. And we can actually extract the regular points from this window of anomaly. And we were hoping that algorithms are going to do better. Then we do data partition as always. Like if you do machine learning, you have to partition your data into training and test, right? Usually, as I say, 80-20. In our case, 60-40 is better. And then we do data processing. We have to do feature selection, right? Because we said not all features are equally important. So I would like to select features that are more important than the others. Why? Because that's going to speed up the process. Less CPU, less memory requirement. Sometimes we do dimension reduction. Even though I have a large data set, I want to reduce the dimension of the problem. Normalization is needed. And then maybe I can also have a model library. So we call it a model ocean. These are pre-trained models. Then I can apply machine learning algorithms, a variety that I mentioned. And a step that's very time-consuming is selecting the best hyperparameters. That's very time-consuming step because we do 10-fold cross-validation in order to select the best hyperparameters. For that, we sometimes use a supercomputer. It takes a long time, but we do insist that we do this in order to be sure that our hyperparameters, these are parameters for the algorithms, are the best. And then we can create the models. And after that, the final step is to use the model in order to do classification. So that's a process. And the tool is put on a GitHub. So as I mentioned, our software is publicly available. More specifically, if we are only interested in data from BGP, from Border Gateway Protocol, there is a subset that actually I put here because you can see all the libraries that one can use. You don't have to outfields. They are collected in binary form. Why? Because that takes less space. But in order to understand what the data are, you have to convert it into ASCII. So we use Zebra dump parser that comes with ripe and outfields data to convert it into ASCII. Then we can do feature extraction, volume, and ASPART features. We create our own tool in C#. Then we can do label refinement, as I mentioned. One doesn't have to do it, but we experimented with those also. K-means and isolation forest. Then we do data partitioning. You can see the libraries that can be used. A lot of libraries out there readily available to the research community. Data processing, feature selection, dimension reduction, normalization, SciPy, PyTorch, then machine learning algorithms. Skitlearn is a library of various algorithms. There is also LightGBM algorithm library, PyTorch. And so this is a little bit about more insight about what tools do we use in order to come to the time when we can actually do classification. But now in experimental procedure, this basically verbalizes what I show you on the graph. First, we do normalized training and test data set. We train the model using tenfold validation. We tune parameters. Then we test the best model. And how do we evaluate the performance? We look at accuracy, F-score, precision, sensitivity, confusion matrix, and very much training time. And I was also talking about the fact that not all features are the same. So this is from a data set that's from a Canadian Institute of Cybersecurity. They have 3 large data sets, 2018, 2 of them, and 2019. And you can see that you can actually calculate the importance of the feature. So for example, the first one is forward segment size, minimum, variety of those. And one can see that not all features are equally important. So why would you waste time in taking all of these features when you can actually probably do the equally well with 8 features or less, because that's going to speed up the process. Why do we do the goal is really to separate blue from red lines. So this is a 3-dimensional graph. You can see the number of implicit withdrawals, number of announced prefixes, average unique paths. These are all BGP features out of these 37. And the goal is to find the combination of features so that you can separate blue from red. Red are class 1 anomalies, and blue are class 0 regular points. Because you hope that if you can separate these 2 clusters, algorithms are going to do better, okay? And for example, this is a Vestrock ransomware attack. You see that its separation is rather difficult, and maybe that's a reason why the algorithms don't do as well as expected when you apply them to ransomware attacks. Performance evaluation, and as I mentioned, I want to show you a graph that we took actually at the broad learning system, an incremental version for this Canadian Institute for Cybersecurity. Did I say 18 to 18? No, there is a 2017, 2018, and 2019 data set. And so let's look at the graph. On the horizontal axis, I have number of selected features. And this specific data set had 78 features. So this is not BGP, right? This is a data set from a test bed. And in this case, it has 78 features. They got a garden variety of denial of service attacks, okay? So we are going to look at the number of selected features. On the left-hand side, we are looking at the performance, accuracy, and F-score. On the right-hand side, we are going to look at the training time. And one can see the tendency. The more features I have, of course, I have to increase the training time, right? So you can see from 65, right? I'm sorry, from 5 to almost 10. And does it pay off? Well, if you look at accuracy and F-score, it pays off a little bit. Excuse me. Because you can see I get a little bit better accuracy and F-score, but it's really worth it. Because maybe with using 16 features, I'm doing equally well. So this is a graph that shows you that, yes, if I take more features, I can do better, but there is a point of diminishing return. Because if you take many features, you have to spend a lot of CPU, you have to spend a lot of memory and time in order to create your model. The red line is for plain BLS, and the blue line is for this incremental BLS. And I'm sorry, the red line is for incremental BLS, the blue is for BLS, and you can see that incremental BLS does better because it takes shorter training time. And that's why we were talking about the positive, the plus feature of the BLS with this incremental property. So you take less time to train the model if you use incremental property. Some numbers, not for you to remember, just to get a feel about what are we talking about. So this is a CNN model. No refinement or refinements of the labels. 2 collection sites, write and route use. Look at the training time, approximately 20 seconds. If you use convolutional neural networks. Accuracy, F-score, precision, and sensitivity, these in red are the best results. So you can get a feel about, we talk about 60% accuracy, 70% F-score, 60% precision, and 98% sensitivity. And the training time of 20 seconds. Very interesting that in this case, refinement really didn't help. And this is why I say refinement sometimes helps, sometimes doesn't. Performance of all these algorithms depends on the data, and it also depends on the problem you're trying to solve. This is GRU and LSTM, right? So in this case, we can see that the training time is shorter. So LSTM and GRU, these are recurrent neural networks. They do better than convolutional neural networks, and they also have a better performance. And for example, in this case, you can see that the model with the isolation forest as a refinement had a shorter training time. With k-means, it had better accuracy. Still, no refinement gave me the best F-score. So everything in red means the best performance. Bidirectional version, better performance, but of course, worse in terms of training time, because bidirectional means you have to run the network back and forth, and that's why it's not surprising that the training time is longer. BLS, this is a flavor of BLS. I didn't tell you about it. BLS has a couple of flavors. RBF stands for radial basis function. And something to notice is that the training time is order of magnitude better. And this is why we were so interested in exploring the new architecture, because it turns out that these networks, they are flat, they are very fast, and comparable accuracy in F-score. Incremental model, especially, you can see the training time very good. And if you add, this is for Western transformer, I think at the end, this was of interest to us. So I'm going to show you really the best performance only for the latest transformer that we studied. If you add the filter, if you add the filter that's going to select the most relevant features, training time is bounded, and accuracy and F-score are doing better. You can do cascades with features, the same idea. And you can do incremental version of features. So you can see that we have done a lot of experiments in order to figure out what is the performance of the algorithms. So with feature filter, you can also do cascades. You can do incremental version as with the original classical broad learning system. About GBDT algorithms, XGBoost. And so look at the training time. Some of these algorithms are even faster than broad learning system, and they have comparable and sometimes even better performance. And our favorite was LightGBM. We are talking about 50 milliseconds for the training compared to 20 seconds that I mentioned for CNN. So you can see it order of magnitude better, very fast. And this is the most important property of LightGBM. And still you can see very, very good performance. CatBoost, cat means categorical. Some of our features are categorical features. And so for categorical features, you do have to convert them into numerical features. And that takes extra step. But CatBoost can do it by itself. So if you have a lot of categorical features, they are not numbers, they are categories. CatBoost can do a good job for you because you do not have to use an extra algorithm in order to convert categorical features to numerical features. So that's the advantage of CatBoost. So to conclude, we evaluated performance of a variety of algorithms: convolutional neural networks, recurrent neural networks, and under recurrent neural networks, we look at long short-term memory. It's bidirectional version, simplified version called graded recurrent unit, and bidirectional version of it. And these are what we call deep recurrent neural networks. And of course, we played with a variable number of hidden layers. These were these little numbers that on my tables that I didn't mention. But you play with a variety number of hidden layers to get the best performance. And something new for most of you, even for seasoned researcher, are these broad learning system models, and they can be used with and without incremental learning. They also add radial basis functions. You can add cascades of map features and enhancement nodes, and you can actually integrate extra trees for feature selection. And if you see this F within these acronyms, that means there is a filter that actually filters the feature beforehand. And quite a bit of work was done using GBDP, XGBoost, LightGBM, and CADBoost. And I mentioned these are very fast algorithms with good performance. So I usually provide the references for people who are interested, or if you are interested to learn more about that. So this is a site for RIPE network collection site. As I mentioned, this is located in Europe. Data is publicly available. They have been collecting this over the last 20, 25 years. University of Oregon Routeviews project also collected the data starting from 2003, also publicly available. NSLKDD dataset is now available from University of New Brunswick. I think it was done at one of the UC campuses, and then they cleaned up the dataset. They made it, it's very important to have a good quality data, and so they did it, and now it's available from them. It's publicly available. I mentioned the Canadian Institute of Cybersecurity, CIC, and they have three collection sites, 2017 and 18, and actually one of the 2018 sites is 2019. I didn't put it here. The pretty graph that I showed you at the beginning of my talk of the internet comes from Center for Applied Internet Data Analysis. It's associated with University of San Diego. They have been doing a collection for a long time, and they had this interesting project called Valrus project, where they actually printed these beautiful views of the internet topology. Tools, as I mentioned, you don't have to build everything by yourself. There are many tools out there: Python, Pandas, PyTorch, ZebraDump pastors. We also have our own tool. We are now changing C# to C++. And actually, we don't really want to convert binary data to ASCII. We want to take a binary data and create the needed matrices with features immediately. So that's one of the projects we are doing now. I believe that data should be posted together with the research results. And so we posted our data to IEEE data port. Check out what it means. It means you can actually port your data to the internet. And so we cleaned up the BGP data sets and we gave it to the research community. So I don't know if it's free. It was free for us to upload, but it's all ready for the analysis. And I also want to acknowledge the data sets broad learning. This is from Philip Chen, who is the author of BLS. They also have the software tool available to the community. So in order to have this idea of reproducible results, that means if I report something in my papers, I would like to enable other people to reproduce them, right? And so in order to do that, you have to share the data. And there is also on IEEE, I think it's called Data Ocean or something like that, where you can upload the software. So not only the data sets, but also the software used. And so that enables the community to reproduce research results, and then you move on with your own contributions. And that's very much different from 20, 30 years ago, when it was really difficult to reproduce results that were published. If you are interested in intrusion detection, these are some specifically readable papers on intrusion detection, and I put IEEE communication lectures, IEEE communication surveys and tutorials, and there is also a RAND Corporation report, and these are usually survey papers because they are easier to read, especially for the beginners, and they all deal with intrusion detection. Deep learning, there are thousands of papers on deep learning. I only posted here what we used. For example, the classical textbook by Goodfellow, Bengio, and Courville, deep learning, right? And also some of the early introduction to LSTM. This is 2017, LSTM was introduced a decade before that. BLS, 2 papers appeared in 2018. BLS was introduced at the little conference in December of 2017 in Shenzhen. But the first journal papers appeared in 2018. And now there are quite a few research groups that actually have tried to apply BLS to a variety of engineering problems. But these were really early publications, both of them in IEEE intersection on natural network learning systems. Because at that time, Philip Chen was editor-in-chief of IEEE intersection on cybernetics. So he didn't want to publish in his own journal. And this is why they show up intersections on neural networks and learning systems. And also, if you are interested in GBTT, XGBoost was introduced in 2016, LightGBM 2017, and this is CADBoost in 2018. So more or less they came around the same time. And very often GBDT does better in terms of speed than LightGBM. We have our own work that we publish. We don't publish as much as we should, of course. We have some journal publications, recently in Communication Magazine. I didn't even realize it was this year, March 23. And in JSAC, 2 book chapters. They are very easy to read because we had plenty of room to explain what we want. The first chapter is about data. The second chapter is about algorithms that we used at that time. So that was work done in 2017. So most of the algorithms I talked to you about today are not there. And of course, conference publications, we do publish quite a bit in conferences, and most of them are already available for download from my webpage. You don't need a login or anything like that. I think the 2 from Honolulu, it was just a conference last month. I didn't upload, but everything else is open to download. So I want to leave you today with a view of the internet. It's also from CAIDA and from this Valus project, just to show you how interesting internet is. And my talk today would not be possible if this Zoom session was not application for, on the one of the internet applications, and both in terms of traffic, in terms of topologies. So it's a rich source of data and information, and very much of interest to both engineering and research community. So thank you very much. I hope I didn't take too much of my time.
Okay, thank you very much, Professor Zajkovic. And it's really interesting materials. I mean, yeah, network is everywhere right now. And yeah, thank you very much for your presentation. It's really interesting. And for all the audience, we are going to the question and answer session. So if you have any question, please just you can raise your hand or you can type it on the chat. Okay.
And I'm sorry for sneezing and coughing, but I got some cold on the way to Indonesia, so bear with me.
Okay, thank you. Professor Zajkovic, I have one question actually. About 7 November or this month, Optus, one of the big Australian telecommunication, they have an outage,
Of 7th of November?
On 7 November, Optus, one of the biggest telecommunication provider on Australia, got an outage. It's about, I don't know, it's about half day. And what I read is it's almost, shut down everything, like the emergency call, the internet, and so on. And the victims, again, it's PGP. I mean, I read some review that the victim is PGP. So about your project, like the Light GBM and the GBDT, they are really fast. And in your perspective, could it be applied on the network immediately? I mean, I think we need something, the data science or machine learning, that can be make alert as soon as possible if something happen on the network. What do you think? Is it possible to make the algorithm applied to the network immediately?
Well, that was our hope, because you would like to install this in real time. And this we were talking about fast algorithms. But we were not really lucky to sell this to anybody. So it's just a research project, right? Because that's why we were looking for fast algorithms. And an early stage of this work, which was already a decade ago, we look at SPM and we realize it's very robust, but very slow. And this is why slowly we were moving to other algorithms. So it would be nice to live GBM, you need 50 milliseconds to figure out that something is wrong. Of course, this is in real time. We didn't notice anything on 7 November, but we are now looking at what happened in 7th of October, because you see, internet and communication is very much used in war situations. And unfortunately, I don't know, you're probably aware that with the war in Gaza, the internet connection was disconnected for the northern Gaza. And so we are now looking at the data collected over the period of month of October to find out if we can say anything. And it's such an unfortunate situation. At the same time, we are interested to find out what happened, right? Can we see that interruption? Can we see the lack of connectivity? And probably we can, right? So at this moment, my group is looking into this. I don't know if we're ever going to find any internet service provider who wants to take the algorithms, but at least, the research community is aware that it's possible to do something like this. There are options you can take in terms of the speed, right? And when you have, like if we create the model library, then you don't have to create the model, because finding a model is time consuming, because you have to select the hyperparameters. That takes time. And for that, it sometimes takes days. But when you have the model and you have the model library, then testing is going to be easier, right? So you have a model already and you can test the model. But it would be nice if somebody would take it.
Yeah. Okay. Thank you very much for your answer. It's really, network is really important for our life.
Yeah.
And
Yeah.
next, it's Mr. Andi Prademon. Raise his hand. Again, time is yours, Mr. Andi.
Okay, thank you very much for the chance. I actually wanted to ask that you mentioned in the page 9 of your presentation that frame 4 and frame 16 have the same pattern. Even if we zoom out, it's still like have the same pattern. And then when we improve in the 64 frames, there might be any noise inside of this pattern of the data, 64 frames.
No, this is coded. So this video was coded. That means I have frames of the video. So I take 4 frames and I calculate how many bits are there.
Yeah. That's the one.
And then I take 64 frames and I take, we didn't think about the noise. I mean, it's basically the frame that I have, and this is what people see, right? Maybe.
Right.
I'm not sure I understand your question. You're
No,
talking about the
I
presence
haven't,
of noise?
I haven't I haven't give any question yet. So I just want to say that this is the fractal time series is actually really interesting, because even if we zoom out, the zoom out, zoom in, the pattern is still there. I mean, like, it's kind of mind blowing for me right now. And actually,
it was very shocking to the.
It's very shocking. This is, I mean, like, very new to me as well.
Yeah, because now I understand you're mentioning noise. That means you can match the traffic pattern with Poisson model with many parameters like a Markov modulated change. So you can match it, but only for that time scale.
Right.
See, time scales are important because some events happen on milliseconds, some event happens on minutes. When you want to bill your customers, you usually take a minute of the call, right? Sometimes the billing is based on hours. So time scale, in that respect, we talk about time scale. So you can model your traffic, Poisson model, on a one time scale, but you cannot use that model for any other time scale.
Right.
So when I showed you the noise in the second graph is basically showing you that that model, which was good enough.
Right.
Okay, I'm really sorry. I think we have a connection problem with Professor Taikovic. Yeah, I'm really sorry, but we have to wait for a while. I hope the connection will come back as soon as possible. So it's really interesting material from Professor Trajkovic, and uh, as everyone see that we have the BGP data, and it's the core of the internet, and then we have the some algorithm like the GPDT, deep learning, BLS, and so on, and it's really great. I hope Professor Trajkovic can be right back, but yeah, we will waiting for them. Okay. And for your information, we have the next session right away after the first session is finished. So, Professor Trajkovic, are you there?
Yeah, I'm here. We got disconnected.
Yeah.
So I just need to finish the sentence to say that people in the statistics departments of Bell Communications Research and even AT&T didn't have the tools to now create new models, because the fractal idea, you know, that Mandelbrot was the father of fractals. He worked for IBM, and he was actually, I mean, there is a history there in the names. But nobody thought about using fractals to model traffic. So it was very much a novelty, right? So people were very surprised that now we have to use fractals in order to understand traffic. So queuing theory anymore didn't work. Poisson models didn't work, right? So the whole theory had to be, so for a while in the 90s and at the beginning of 2000, many people were trying to actually use fractals in order to do traffic modeling, create synthetic models. So even the statisticians were surprised that now you don't have any more closed form solutions, right?
Right,
Queuing theory doesn't work anymore.
Yes, yes. There are many more algorithm and method we can use actually. About this, you talk about machine learning algorithm, which I also feel interested in this kind of topic. And I feel like human, because machine learning is trying to duplicate human brains. And the way I think, like human actually learn everything when they see, they learn from the listening from everything. And I thought like we could also make this kind of model that we directly can learn from this activity. The thing is, I know that there is a transfer learning that we can directly learn after training the model. We can do training again, using the pre-trained model. And but this kind of model has difficulty on when we retrain. It takes a lot of time, a lot of days, sometimes weeks to train, because it's a very huge data. So how do you think about this continuous learning?
Well, I think it's interesting. It's novelty, and people can work out to find out how to make these models more useful. There is also federated learning, right? So there are all sorts of options that people use, especially nowadays that you can't really compete with the companies and universities. Companies have huge resources, right? And universities don't have it anymore. So maybe go to the cloud and actually, but nobody wants to give up the data, right? So there was an option like, you give me the data, I'll give you the data and you give me results, but that's not something that people want to do, right? But creating a model based on the data and then sharing the model, it's a different story.
Right. The pre-trained model.
Yes. But transfer learning, I think when I was giving a talk in Honolulu last month, somebody also mentioned transfer learning. So there are all possibilities, right?
Right. The thing is, the learning process is just too much. It's too much time to wait.
Yes.
So yeah, I feel just like if we could shorten this time, we could just do the continuous transfer learning. So this kind of algorithm.
Especially because you want to do this in real time.
Right. That's the real problem.
You want to do this in real time.
Yes. I think that's where we are up to.
Yeah.
Okay. Thank you very much for the discussion.
Yeah. Thank you for asking.
Okay, thank you very much for Mr. Andi Pradama Yunus, and also our distinguished speakers, Professor Shaikh. To be honest, it's really interesting materials because yeah, like you said, internet is running the world right now. Without internet in 1 hour, we like it's dooms, right? So, but we know that BGP still have like of security. We still
Oh yes,
need to improve that.
BGP is an old protocol.
Yeah,
It was invented at a time that nobody thought about security. When internet was put in place, nobody thought about security because it was really meant for close group of researchers. Nobody envisioned that somebody is maliciously going to put worms or ransomware attacks. And so BGP became a routing protocol. There were other proposals, but they never took off. So if you look at the BGP, right, there is no security in BGP. And so this is why it's very vulnerable to attacks. But I'm going to look at the November, you said November 7 in Australia?
Yeah, Optus, the provider is Optus. Optus Internet
How do you spell it?
Providers. Optus.
Optus.
OPTUNS.
Okay.
Okay. I think
Optus.
it.
Okay, I will
Optus,
look
yeah.
at this.
Yeah. I think it's the end of our
you.
first session. Thank you, Professor Taikovec. It's really a pleasure to be your moderator. It's pleasure for me. And thank you very much for the audience. And I will give back the time and the screen to our Master of Ceremony. Thank you very much.
Thank you very much. Thank you.
Okay. Thank you to Prof. Luliana Trakovic for the very insightful session. And thank you for Mr. Mega Pranata for moderating our first keynote session. Okay, now let's transition to our second keynote session titled Why, Can, and How Research with our esteemed speaker, Professor Xu Yu. And the session will be moderated by Mr. Andy Pradimon Yunus, PhD. To Mr. Andy, time and screen is yours.
Okay, thank you very much for the MC. I would like to open this session. We have two sessions in this keynote speaker session. We have one presentation from Professor Sui Yu, and the second is the question and answering session for 15 minutes. And I would like to ask if Professor Sui Yu, are you there?
Yes. Can you see my screen?
Yes, I see your screen right now. How would you like us to call you, Prof?
You call me Sri.
Okay. Prof Yu is okay?
Yeah, it's okay. Because I do not have a headset. Sorry for that. So I have to use my computer.
Okay, thank you very much. I would like to thanks the organizer of these events from the IEEE Communication Society Indonesian chapter, the Indonesian section of IEEE AESS and GRSS and Institute Teknologi Telkom Purwokerto, and the technical sponsorship from the IEEE Indonesia section and co-hosted by Institut Teknologi Telkom Surabaya, Institut Teknologi Nasional Malang, and Polytechnic Negeri Malang, and patroned by Telkomsat and KeySite. And I also would like to thank and welcome Professor Yu in Indonesia. How is your day in Indonesia, Professor? Is it good?
Yeah,
okay. Do you like Indonesia?
Yes, very much similar to Sydney at this moment. Thank you very much.
So right now I would like to introduce Professor Sui Yu right now. Professor Sui Yu is a professor of School of Computer Science in University of Technology, Sydney, Australia. His research interest includes cybersecurity, network science, big data, mathematical modeling. He has published 5 monographs and edited 2 books, more than 500 technical papers at different venues such as IEEE, TDSC, TPDS, TC, TIFS, etc. And Professor Yu also promoted as the research field of network for big data since 2013. His research outputs have been widely adopted by industrial systems such as Amazon and Amazon Cloud Security. Wow, very amazing. He is currently serving the editorial boards of IEEE Communication Survey and tutorials, and IEEE Internet of Things journal as the editor. So today's topic is about why, can, and how to research. First, I would like to ask, like, maybe some of us still a junior or young researcher, or even a PhD students, or even undergraduate students. We may have questions like why we do research, and if I do this research, can I do this excellently, and how to do the high quality research. This topic will be presented by Professor Yu in here. I would like to welcome Professor Yu. Times is yours.
Thank you, Andy, for the kind introduction. I believe you guys can hear me, right?
Yes, Professor, we can hear you.
Okay, so the title is why? Why do research? Can we do research? How to do research? Why I give this talk? Because my background is China, mainland China. I got a lot of friends. The young people, they ask, when I graduate, what should I do? Should I go to the industry? Or sometimes I want to do research, but I'm not sure. Can I do it or not? Right. So this kind of questions they ask. I say no one can help you to make the decision, right? But we can offer you some information. That's the reason I give talks about it. Okay. First of all, I also want to introduce a little bit about my university because they pay my salary. Okay, the university is called University of Technology Sydney, which is ranked 90 this year, and our computer science is ranked 17 worldwide. Okay, so welcome you to study with us at UTS. The point of this talk, okay, only 2 points. The first point is a senior undergraduate student can do good research already. For example, in China, or the undergraduate study is 4 years. In Australia, 3 years. Usually in the third year, the good undergraduate student, they can do good research because there are some successful examples, right? I can list a long list, but not too many. But there are some on the year 4 undergraduate students. They publish papers on the top journal or top conference in computer science or telecommunication. So someone proved it, right? Then the second question is, if we want to successful, what are the conditions? Based on my understanding, there are 2 conditions. One, you need on the right track. If you're on the right track, you need another condition, sufficient effort. Right. If you want to be successful, you have to have these 2 conditions, on the right track and sufficient effort. How can I on the right track? If you're a genius, you don't need someone else. But for most of us, we need a teacher or a supervisor to keep us on the right track. How can we invest sufficient effort? No one else can push you. That's dependent on yourself. Okay. So if you have some other business need to do, you can leave now. So that's the point of this talk. Okay, that's the point of this talk. If you believe it, then you can leave now. If you don't believe it, give me another half an hour. I will let you know why I'm correct. Okay. So that's the outline. Okay. The first question, why research? Right. You may know the recent story about OpenAI. OpenAI, the company, they fired their CEO, right? And then the next day, Microsoft said, we hire him. Then he will take, say, 70 OpenAI staff with him. Microsoft offer each one of them $10 million US. Right. But things changed the next day. OpenAI said, okay, then you guys come back. Okay, the Adam will be the CEO again. So what does that mean? That means in this century, the most important thing, value, is people, smart people, the people, capable people, not your neighbor, right? So how can I get the most important thing is the capability. Yeah, I would like to ask the audience to mute yourself if you do not have questions. Okay, thank you. So the most important thing is the capability of solving problems. Then how can I have the capability? For example, a doctor, if you have a headache, then you see the doctor say, okay, your headache, you have some Panadol, then problem solved. You have stomach ache, okay, he will give you some other medicine solved. Back to three or 4 years ago, when we have COVID, then you see the doctor, can you fix my COVID problem? Doctor cannot, right? So if at that moment you can say, I can have something, can fix COVID, then you will be the richest people in the person in the world, right? So, okay, that's the difference. Okay. So how can I get the capability of problem solving? That's research. Okay, research can help you gain the capability. Capability is more important than knowledge, my friends. What is knowledge? What you learned in the primary school, high school, even university, that's knowledge. Knowledge doesn't mean capability, right? So, for example, we have new COVID, then can you find a medicine to fix it? That's the capability, okay? The doctors, what they use their knowledge to fix our medical problem, that's knowledge, not sort of a capability of what we want. Then how can we gain the capability from research? Okay. Can we do good research? The answer is yes. Why? For the senior undergraduate student, for example, year 3 undergraduate student, compared with the PhD students, obviously the PhD students have more knowledge. However, in order to solve one specific problem, then the knowledge we need is fixed. For example, knowledge for the paper is this rectangle. We know something about it, but there are also something unknown, right? So what you need is you need to learn the new knowledge to make this rectangle full, then you can solve the problem. So for a specific problem, an undergraduate student and a PhD student, they are almost at the same start point. So research on one given problem, there is no big difference between an undergraduate student and a PhD student. What you need is you learn the new knowledge to make this rectangle full. Okay. So how to research is simple. If you don't know how to do research, you think about how the sports person, the swimmers, the badminton players, how do they train themselves, right? So I believe the sports people, they train their body, they train their muscles. For us, we train our brain. Essentially the same thing, right? If you want to get Olympic gold medal, you know Australia is very good at swimming. The swimmers every week they train 17 times for the 50-meter freestyle swimmers. Every week they train 17 times. Each session, they swim 10 kilometers. That means if you want to join Olympic, you have to, for the 50-meter butterfly or backstroke and whatever, every week you have to swim 170 kilometers every week, right? That's the training level. You say, okay, I only swim say 10 kilometers per week, then you want Olympic medal. It's almost a daydream, right? So you have to train harder. Now our research environment is actually very good, right? Usually we have digital library. I'm not sure about Indonesia, but I'm sure in Australia, wow, the environment is very good. If you want to check the digital library, no problem. You want to print, you want a book, no problem, right? So the only missing piece is our hard work, right? Okay, then when you do research, then we need to measure. When you graduate, for example, you do undergraduate study or you do a master or PhD. When you graduate, you go to the job market, you want a job. Then your potential boss, they will measure you, right? The easiest way to measure you is publication. What kind of publication do you have? What's the quality, right? So that's the reason at the end of this talk, where I will talk a little bit about paper writing. You cannot say I'm very good in research, but people need evidence. If you have high quality publications, then that's the evidence, right? But high quality publication doesn't mean this guy is a high quality researcher, but somehow means something. When we talk about publication, we have an ethic issue, right? So because this talk we do not involve too much, so you cannot cheat, right? So plagiarism is not acceptable. Yeah. Okay, I suppose so far you believe an undergraduate student can do research, can do good research. Then the next problem is how can we do research, right? I think for most of us, we do need a supervisor. The supervisor can see which way is the correct way, which way is the incorrect way, right? That's because when we are young, for example, 5 years old or 7 years old, we do not understand the word correctly, right? So one day when I walk on the street with my son, he was say 7 years old. We see someone using airplane to write characters on the sky. The first letter is M. He asked me what the rest of the letters. He thinks it's McDonald. I said no, definitely it will be marry me. Then it turns out I'm correct. He was very surprised. How do you know? I said I just knew it because I saw it. I saw it before. Right. So as a young researcher, I think you do need a supervisor who has experience, he or she knows what ways are the correct, what are the wrong ones. Okay. And so the research essential. First of all, you have to decide a suitable direction. If you want to do a research, first you need to decide a suitable direction from your supervisor. There's a lot of things we can do. For example, in computer science, well, the quantum computing looks fancy, right? So I want to do it, but is it suitable for you? It is good, doesn't mean it's good, it's suitable for you, right? So if you don't know quantum physics, or your supervisor doesn't know quantum, you'd better give up. Even it is very beautiful, you have to give up, right? So you have to find a suitable direction to do. Okay, so for example, AI is beautiful, but in AI we need a lot of computing power. In your lab, do we have the computing power? If we do not, then you forget it, right? Second, well, you decide, okay, I will do AI, okay, AI, because AI is hot, AI will help me find a good job. That's good, great, okay. Then we need to identify a suitable problem. In AI, there's a lot of problems, theoretical problems, right? Application problems. For you, you have a lot of conditions, constraints, so you need to find a suitable problem. So you should work with your supervisor to find a suitable problem. Okay, once both of you decide the problem is suitable, then if you knew everything already, then that problem is not a good problem. In terms of research, definitely there is something you don't know, right? So now the step 3, you need to obtain the necessary knowledge by yourself, right? Someone said, I have this problem. I hope my teacher, my supervisor, he or she can tell me, can teach me. I can tell you the truth, my friends. Most of the time, the supervisor, we don't know, right? So you have to depend on yourself, right? Not always, but most of the time, we don't know, okay? Of course, when you do research, you have some obstacles, right? Someone said, I have a lot of experience with this. One of the young PhD student discussed with me, said, Professor Sri, I cannot do my research well because I do not have sufficient people. If my supervisor give me a few master students, help me to do the experiments, I will do my research very well. I say, okay, you sure? If your supervisor really give you a few assistants, I don't believe you will be successful, right? There's also sometimes they also ask some other questions. Say, I cannot publish high quality papers because my English is not good. If my English is good, then I should be able to publish high quality papers. I say, okay, that's easy. You write your paper in Chinese or in Indonesian. Can you publish the paper in the top Chinese journal or top Indonesian journal? I don't think so. So I don't think it's a language problem, right? Of course, language is sometimes also an issue. Okay, anyway, there are a lot of obstacles when you do research. You have to fix them. Then you have to demonstrate the advantage of your research. Everyone claims his research or her research is great, but how can the reviewer trust you, believe you, right? You need evidence. Okay. Then you need after all those, you need to write a paper or make a prototype if you want to do startup, right? Okay. Strategies. The first strategy I suggest is be positive and target high, right? So you Well, some students said, oh, my university is not good. My supervisor is not the top researcher. So I suppose not do good research. That's totally wrong, right? You have to be positive. Why in the Olympic game or other games, the sports person usually they tell themselves, you can do it, right? That's the positive attitude. I can tell you experiments did by Science. There's a paper published by Science. They have two groups of people. They ride bicycles. So the first group, they just tell nothing, right? They ask, there is a hill, ask the people to ride up to the hill. There are two groups. The first group tells them nothing, okay, then record their performance. The second group, before the riding, the organizer gives them pills or drinks, tells them, okay, you drink this this can improve your performance. Actually, the drink actually water. But you guess what? Psychologically, the second group, they believe they had something. Then the result is the second group performance is better. That's the positive attitude. Okay. Second thing I want to let you know is to tune your attitude. When you do research, it's your own business, right? You cannot depend on someone else. You say, oh, someone can help me to collect the data. Someone can help me to do the programming. Then it's impossible, right? So you have to do everything by yourself. If not everything, I think 95% of the work you have to do by yourself. You have to depend on yourself, okay? And also be active, right? So you cannot wait for your supervisor to push you. You have to push the supervisor, okay? And then be adaptive, right? And you know, not the smartest animal survive, not the strongest animal survive. It is the most adaptive animal survive. So when you do research, there is no answer. No one knows this way will lead to success or not. So you have to be adaptive. How? Then we don't know, right? As a young researcher or a beginner, so I suggest you following first, accumulate to be creative. So sometimes the young researchers, they say, oh, Professor Shui, you see this area, no one did it. I read a lot of papers. No one did it. We do it, right? Create something new. I say, okay, you'd better stop it. Right, why? Because there's so many researchers, they are so experienced, they didn't find it. As a newcomer, how come you find it? If you find it, there's only two possibilities. One, it does not work to do it. Two, it is too hard. They cannot do it. Right. So when my son is very young, he usually brings stones from school and show it to me, this treasure. Okay, Jim. I say, great. Okay, we take it. Right. Okay. So when you are beginner, so you'd better following first. In this area, who are the top researchers? What are they doing? Right. Because usually they know the field very well. So they can find the reliable places, directions to go. So you'd better know, for example, in my area, for example, privacy, who are the big players internationally or nationally, right? So you try access their website. What are they doing? Okay, sometimes you may talk to them. For example, during the conference time, you can ask them, okay, I see you are doing this research. I'm very interested Is it a good direction? Sometimes the professor said, no, this is the last paper we write. We finished 2 years ago, right? Okay, so first you should follow rather than accumulate. Okay, because the second strategy you may not understand because I give this talk to the Chinese community, so they have a story. Say, okay, I skip the story. Every Chinese students, they know this, but the second strategy is the journals. Usually we have a ranking. Say, okay, this kind of journals conference, they are A, those 3 B, those 3 C, right? If you want to publish papers in the C ranked journal, you'd better read the papers of the A and B and then submit it to level C. That's called Tian's house racing strategy. That means when you do your training must be harder than your target. Or I make this way: if you want to get the championship in badminton or other sports, for example, swimming in Indonesia national game, you'd better join Olympic, right? When you train yourself, you have to train at the Olympic level. Then you join the Indonesia national game. Then you, with a high probability, you will get the championship, right? If you only train, you target on the Indonesian national championship, you train yourself, I guess it's not easy to get the champion. So your training must be higher than your target. Another strategy we are using is called a paper submitting based training. When you do your training, say every year, if you want muscles, right? You have to go to the gym every day. Every day you train maybe 1 or 2 hours. Then you can have 6 packs on your belly, right? So paper submission publication, similar thing. So every year in my group, I ask my PhD student, every one of you have to submit 4 brand new papers to 4 high top value, either top conference or top journals. If the paper rejected, then we know the difference. But where are we? We know where are we, right? If you, for example, you submit a paper, get 3 rejection, that means you're very bad. Then second time, you get 2 rejection, 1 accept. Okay, you are getting better. Then third time, you get 1 reject, 2 acceptance. Then you are getting better, right? So if you keep trying, then one day or the day after, tomorrow, you will get a paper accepted. So you have to submit sufficient papers to communicate with the community, then to see where are you? Okay. Professor Liliana is EIC, so I want to she will make comment for what I talk. Okay, at the end of this talk. Another suggestion is read high quality papers, a large number of high quality papers, right? Usually 50, I think 50 plus is the number we expect. As a new researcher, you have to know the place very well. There are some students, they read a few papers or 5 papers, they say, okay, sure, I know how to do research. I have an idea. I say, no, hold on, not hurry, right? For example, you come to Malone just a few days, you say, okay, I understand this city. It's not true. You have to stay here. You have to travel around. You talk to different people, say 1 or 2 months later, you may say, I understand Malone. I understand, say, Indonesian culture, right? So you cannot talk to a few Indonesian people. You say, okay, I understand the culture. It's impossible. So that's the reason you have to read a sufficient large number of high quality papers. One of my students said, when I read the high quality paper, I have headache. Right? When I read the low, say, level C papers, I understand. I feel I learned something. Okay, I say, okay, you come here to get my training. Is it a holiday, or you want the training, or you want treat Sydney as a holiday venue, right? If you want training, you want to get to the Olympic championship, you have to do it, right? I'll say at the end, most of them will follow my instruction. Read hard, right? Okay. Research by doing, not only thinking. Someone said, I will think. When I have a brilliant idea, then I will start to do the research. So that's not correct, right? When we think, sometimes the idea may be not correct. So you have to do. When you sort of have some ideas, then you need to start to hands-on to do the research. When you do it, you may find new problems, new solutions, right? When you have no idea, the experiments failed, the theory failed, you feel frustrated. You have you find that nowhere to go. What should you do? This time, you repeat to read papers, right? Okay. Of course, sometimes you can also pray, but most of the time, I think God doesn't listen, right? This kind of pray, they do not listen. Okay. Okay. The last part, I want to take a few minutes about talk about paper writing. So, well, you did research. You want get some evidence about your research. Then you have to publish papers, right? From another perspective, we need communications. When we publish our papers, then people will read it. People may comment on it. Then there is a communication in the community, right? And also promote researchers. Okay. When we write papers, a lot of young people, they say, my paper always be rejected, then reject again and again, right? Very frustrated. Okay, so then I ask one question. When we write a paper, when we do the research, okay, we seriously do research. We have our strategies, our methodology, right, doing research. But when we write a paper, guys, it's another business. So I ask you, what is the most essential purpose when writing a paper? Well, someone said, oh, I will deliver my knowledge to the others to benefit the community. That's okay, correct? Right? Someone said, I want other people know this knowledge. That's correct. But I tell you, from my opinion, that's not the most essential purpose when you write your paper, right? Then you may ask me, what's the essential purpose? The goal of paper writing is get the paper accepted. Okay, that's the goal. So if you say, I want to deliver my knowledge to the people, then when you write a paper, you write a lot of unrelated things. You write the background, write a lot. You want to deliver the knowledge to the readers. However, when you send your paper to the journal or conference, you want your paper get accepted. In other words, you sell your paper to the reviewers successfully. So the 3 reviewers, they will represent the community to decide is this paper should be rejected or accepted, right? So then when they make, how do they make the decision? They read your paper, try to find the evidence. Should I use those evidence to reject the paper or accept the paper? So when you write the paper, your most important thing to sell your paper to the reviewer. At this moment, you don't care about the readers. If your paper is not published, readers will never read it, right? So you have to first persuade the 3 reviewers. So my philosophy of paper writing is persuasive writing with evidence. When you write your paper, you have to persuade the 3 reviewers. Okay. Of course, how to persuade them? You need evidence. Okay, my friends. Someone said, okay, why we persuade writing? Right? That's a, okay, my research is correct. Then they should be published. I tell you, Einstein's paper was rejected. Do you believe the special relativity was rejected? The information theory by Shannon was rejected. One of the comments said, now everyone is researching on colored TV. Your paper is not attractive, right? Okay, so why persuasive writing? Science is objective. 1 + 2 always equals 3. 1 + 2 = 4. 1 = 5. 1, right? So science is either wrong or correct. However, paper reviewing is subjective, right? This paper is it good or is it very good? It is subjective based on the mind of the reviewer, right? For example, you say, okay, Professor Yanas, okay, Andy, is he handsome? Different people have different opinion, right? Okay, that's subjective. So that's the reason you have to persuade the reviewer. My paper is good enough, right, to be accepted, right? Okay. Of course, that's the last slide I used. So if you want to do study with us, you are welcome to contact us to study at Sydney or Vancouver with Professor Liliana. Okay, thank you very much. I would like to take questions if you have.
Thank you very much, Professor Yu. I would like to call you Professor Cool because you are so cool.
Thank you.
So opening the question and answering session, if you could, you can just raise your hand if you want ask any question. I give 30 seconds to receive one question. Okay, it's 30 seconds and no one giving the raising hand. And actually, I have so many questions, Professor Cool. One of my friends actually telling me that research is actually two different words. It's re and search. So we do search several times with iterations. How many iterations we don't know. So this kind of philosophy makes me like, oh, even if I got rejected, that means that I have another iterations to be accepted. So this is a new effort as well. How do you feel about this?
Okay, you repeated the question again.
Yeah. How do you feel about this philosophy of doing research is separating words of re and search?
Yeah, I heard about it. I agree. So sometimes you think it's correct, but later on, for example, at the very beginning, people believe the Earth is the center of the universe, right?
Right.
Then later on people think the sun is the center of the universe, and then later on think sun is not, right? That's the research.
Right. So I'm very deep believe this kind of thoughts as well.
Yeah.
So actually, we have quite enough time to discuss about many things. You just present for 30 minutes, and we have 1 hour. Actually, we have 45 minutes to go with the question and answer. I have another question, Professor. For one of my professor when I do PhD in Japan saying like new graduated PhD know the novel method. That's why now better novel methods than the other professor, let's say. That's why PhD students or even master students is needed in the university. For this kind of statement, would you like to offer or open your university or your laboratory for the Indonesian student to do PhD and master there?
Yeah, of course. We do. We have a lot of good staff, and I believe I'm a sort of good culture. I just like the soccer culture, right? So I need 22 people to go to the World Cup, but so far we do not have 22 people, right? So we welcome more, say, young people who wants to be excellent, who wants to be successful to join us at UTS. Yeah.
Right, you hear that, everyone. You can just, how do we contact you, Professor? Maybe you can just find it in Google. I think Professor Suyu's contact is everywhere in Google. So, yeah. I actually have another question. My department head just asked me to ask this question for you. How do we know that our research has made an impact? Like, is it enough if we only know from a number of citation only? Like, how is the metric? How is the citation impact our paper?
Oh yeah, that's a really good question. So how do we decide our impact? I guess that's very hard. That's a very hard question, right? Because especially in our field, because it's hard to measure. So sometimes people have to use some metric. So then citation becomes the metric.
Right, citation sometimes becomes metrics, Professor.
Yeah, sometimes it becomes a metric, but citation doesn't mean citation is correct.
It's correct, but I feel like the impact of the citation sometimes doesn't mean that the paper is actually really good, because like if we have a very good paper, very good evidence and everything inside the paper, sometimes the applications is just so less, so not so many people cite it.
Yeah, we just check if you check the citation of the Nobel laureates, you will find that I guess their citation are not good. Right.
Right. Yeah. And also, like, if we try to find a really good journal on impact factor, we want to see impact factor in the journal. Sometimes the impact factor doesn't mean the paper there is also really good, because I feel like the paper of Attention is All You Need by Google Transformer, they publish in the archive. not even a journal, it's just a preprint journal, and they have really tons of citations. So I feel like this kind of metric of citation is sometimes good, sometimes not necessarily means it's good.
Yeah, so depends on where you use it, right? Someone said, okay, the top class university, for example, Harvard, they don't count citation. Okay.
I see.
Yeah, so the second layer university or the third layer university, we have to use citation as a metric.
Right. Because this is one way to measure.
Yeah.
And is there any other question from the audience? If not, I will just ask one more question to Professor Yu. Actually, these days I heard like several students they are just a third semester in their third or fourth semester in the undergraduate students. They are undergraduate students, and they want to be so focused on the certain study or certain topic, And I feel like it's not necessarily like that, because we actually on that stage, they can, like try another focus, try another study, and try to find something really lovable topics. And how do we choose this? How can we get these directions? How can we get this focus?
Yeah, that's a good question. I have my understanding. Some students say, okay, I don't like this topic. I want to change it to another topic. Right now, hey, quantum computing is popular. I want to do that. Can you support me to do that? I say, okay, you can do it, but I cannot guide you because I do not have the knowledge. Right? However, I say, okay, you do say privacy with me. So the whole procedure is training to gain the capability of research. When you graduate, you find a job as a lecturer. If you want to do quantum computing, then it's your choice, right? So when you do PhD with me, we treat it as a training. Doesn't matter the topic is what. You gain the capability to do research. Then when you graduate, you can choose other topics. Someone said that we have to choose a new topic every 5 years in our domain, right? You cannot always, yeah. For example, in our networking domain, well, people first doing P2P, then now P2P is dead. People doing recognitive radio is dead already, right? So you have to be adaptive.
Right. We need to be adaptive, even if we are a doctor. Actually, I mean, like PhD students already, we still can change our focus, right, Professor?
Yes, you have to. Some big professor told me you have to change your topic, shift, not change, right? Shift a little bit every 5 years. Otherwise, you're in big trouble because after 5 years, the topic is getting old, cooled down. Then it's hard to get funding or publication.
Right. It all goes to funding after all. Yeah. How about the other audience? Is there any question for this session? This is a very interesting topic to discuss, because this is actually the fundamental of going to the academia or going to industry, because we need to do research first. We need to do how to do study first. Yeah, just like
Yeah, okay. I may not make this clear in the Chinese community, because you go to industry, a lot of money, right? The kids, the young people, they are hesitant. Well, the parents want them to do, say, PhD, but they want to go to the industry to have money. Okay. Then they ask me, okay, I don't know which way to choose. I say very simple. Okay, you invest your money to buy some stock. You do investment. You have the risk to lose the money. But you invest your money in education, you will never lose. So right. The answer is very simple. You should do PhD, guys. Right.
You hear that, all of people here. You all guys should go to PhD, and Professor, you will try to guide you.
Yeah, come to Sydney. We train together. We explore the future unknowns.
Right. Thank you very much for this very interesting topic.
Maybe I can say something. Since I'm sitting here listening.
Time is yours, Professor Liliana.
Thank you. Thank you. I think there were a lot of questions that were asked, and I'm sort of thinking about how did I deal with my students. I had students who wanted to change a topic every 3 or 4 months. So he was a master degree student, not bad. He did well in courses, but every 3 months he would change a topic. And I finally had to tell him, for your master thesis, you have to stick to one topic. Because doing master thesis, it's research. It doesn't mean that it's this kind of learning experience when you just jump from a topic to a topic, because you will not get results. So that was one of the experiences about changing the topic. I think there is echo here.
I'm muted. Muted.
Okay.
Mm.
Much better now. But in terms of area, our area is such that we really every five years have to shift a little bit. Of course, it's very difficult to completely change a topic. Like I have two different fields. My PhD was in dynamical systems, classical circuit theory. So when I graduated, there were no jobs. So I went to work for Bell Labs. I worked for a computer-aided laboratory. And then I implemented some of the things I learned in my PhD in a software tool, right? So it was a sort of mathematical approach. And then I decided, okay, Belcor was basically sold. I had to go to academia, and I always wanted to go to academia, and I had to change the topic already when I was in Belcor to go to communications. And it was really very difficult. It's very difficult to change drastically a topic. And this is why Professor Yu was saying, you change, but you still keep the basis, right? But you shift, right? So I remember having a headache for 2 years because I had completely to change the topic from dynamical systems to communication networks. And it was not easy. And I really never felt I got the recognition in communication networks as I did in nonlinear systems. But it's a reality. There were no jobs in nonlinear systems. Nobody would offer me a job, right? So moving to a field like communication networks, which was really a hot topic 25 years ago, and there were students and there was funding, especially networking, was a good decision. It was just very painful. So now what I do, like every 5 years, I change a little bit. First, I study the protocols, simulation of protocols. Then I study traffic, which I started in Belcor. Then we moved a little bit into machine learning. And so now I'm moving into brain-computer interface because it's also connected with signals. And so we are trying to apply some of the machine learning algorithms to the BCI or BMI. BCI stands for brain-computer interface and brain-machine interface. So I want to capitalize on the knowledge that I have, move into slightly different fields. But jumping from one field to another is a painful process. That was my experience. I just wanted to add it. So thank you.
Professor Yu, you want to respond to Professor Liliana?
Yeah, absolutely. I totally agree.
Right. I mean, like Professor Liliana, if you change drastically, I know the painful of the learning process that you need to take. But
yeah.
the way it's like 2 years of changing and 2 years of headache, we also need money, isn't it?
Yeah.
Yeah, so I needed a regular job, right?
Right.
Because I was a visiting professor in Berkeley and I didn't want to go back to industry. I wanted to go to academia. And in Belcor, I already started because Belcor gave up on building software tools, CAD tools, and we moved into traffic analysis and traffic collection. And so I sort of already in Belcor start moving into communications. But when I was on my own, it was difficult. It was difficult.
It was difficult. Yeah, I can feel your painful there.
But that was a long time ago. That was 25 years ago.
Yeah.
But honestly, I still feel more comfortable with dynamical systems, maybe because I was younger. And this is where my formal training was, because I studied with a quite well-known professor at UCLA. And it was just a beautiful theoretical subject, nice theorems, mathematical applications. We even found applications in computer-aided design tools. It was dealing with homotopy, continuation methods. So I still feel very emotionally connected to the field. And so maybe it's what people call the first love, right? So
okay, that's the first love of your dynamic theory.
That's right. So
that's right. Okay. Thank you very much for your insight, Professor Liliana. Is there any other question from our audience? I would like to mention from the ITN. How about from the ITN? Any questions, guys? Remember, this session is just a quite casual session. You don't need to be formally asked the question. Prof, you are still mute.
He was my host.
Oh,
But
Okay.
he has his hand up. You have your hand up.
Mm.
right. No one looks like trying to ask something. Oh, Mega Pranata is raising a hand, please.
Okay, to be honest, it's a really interesting topic. I mean, jumping from one topic to another topics, I feel the headache right now because I'm still finding PhD supervisors and also the scholarship. And I mean, what kind of sacrifice we should do for that? I mean, jumping from one topic to another topic, it's really painful. I mean, we should learn about everything new. And from your perspective, Professor Yu and Professor Taikovic, it is okay to we just how far we can move or we can pivot from our interest right now to the new interest for pursuing PhD. I mean, for finding uh, the I mean the best supervisor and so on. So how far we can move? I mean, how far we can just pivot from current interest topic to the new topic for pursuing that. Thank you. I think that's my question.
Yeah, that's a good question. Professor Liliana, do you get some answers?
Yeah, I can say something about it. I had a student who came as a designer. So he actually got a master's degree already in Europe, but he was designer. And so he wanted to move into communication networks, and it took a long time. It took him maybe 7 years. Maybe if he was if he had a different lifestyle, it would be less than 7 years because he got married, he had a family, but it takes time. The good thing is when you go through your graduate studies, it's easier to change because you are a member of a team. You have an advisor. See, when I was talking about the change, this was way after I got my PhD. I already had my PhD. I worked for 5 years in industry, right? And within like 2 years, 3 years, I had to change the field. So it was basically done on my own. But if you are looking for PhD, for graduate studies, that's much easier because you will choose a professor or the professor will choose you. You are going to have a team. You have to have somebody who is going to guide you. So it doesn't have to be 7 years, like in the case of the student I'm mentioning. It can be shorter, but it's much easier than changing a field after you have your PhD and after you get a job. Within PhD, you are part of the system, part of the team, right? You will be taking courses. Like at SFU, you have to take a certain number of courses. And then we will be working on a project. I usually ask students to work on a project now from the very beginning. I didn't do that when I was a younger professor. I would let the student take courses for a year, and I realized not a good idea. So now I try to involve students immediately, right, from the very first day as a part of a team, because I don't know if all my students agree about the teamwork, but yeah, I run my lab as a team. And of course, when you work with people, there are always issues, but somehow when you're part of the team, you learn from other team members, right? And so the other team members also guide you. Like you feel down, you don't feel like working with them, but you see your colleague is working, right? So much easier to change when you are a graduate student. That's my experience. And feel brave to change. It's doable. I mean, especially in North America, I don't know how it's in Indonesia. In Europe, it's difficult. So in North America, you can say, I want to do something else. So I'll give you an example. My bachelor degree is in power engineering. So I would never be able to do even nonlinear circuitry, maybe, or electronics or communications with my bachelor degree in power engineering, because the system is very traditional. You have your bachelor degree in power engineering, that means your master degree, your PhD, and your job, it's all going to be in power engineering. But in North America, it's different. It's much easier to change. Let's say I got a bachelor degree in power engineering and I decided I'm really very interested in communication networks. So I'm going to find a professor who is going to accept me, hopefully fund me. I'm going to be part of the team and I can move on. In Europe I don't know how is it now because I left a long time ago, but it was expected from me with a degree in power engineering, high power, generators, motors, transmission lines, right? It was expected that I would be continuing my education as a master's degree student and PhD student in power engineering, but I didn't do it because I got interested. I was always interested in circuit theory, but then I got interested in computer engineering. So one of my master degrees from Syracuse University was computer engineering. I got interested in computers, and it was doable.
Right.
I don't know if Professor Shook has anything to say.
Professor, you, would you like to respond?
Oh, okay.
Are you muted?
No, just my computer is running low power. Okay.
Oh, do you have the plug?
Okay, that's okay. Okay. I just okay. My computer just running out of power.
Right. Okay. Maybe.
Okay,
yeah.
still okay. We still can hold for a few minutes, I believe.
Okay. Maybe you can respond to this. For changing and pivoting, how scary or how much effort we should do, what should we sacrifice?
So you're asking a question, right?
Yes, from Mega Pranata's question. Actually, it's just Professor Liliana already answered the question, but
yes.
how about you?
Well, I think it is. It's not easy, but I learned one thing from the big professor. He was Ivan Stojanovich. He said, "Okay, we have to change this." I said, "How?" As a young faculty member, he said, "Okay, we use 80% of our time to do our current topic, use 20% to explore the new topic, and then decrease the current percentage and increase the well, after a few years, then the new topic becomes 80%, right?"
Right. Right. That's how shifting does.
But he actually did very well because his degree was in mathematics. And then he moved into wireless networks and he was very, very successful.
Oh, that's very nice to hear. What a very nice experience. Is that answer your question, sir? Mr. Mega Pranata?
Okay, thank you very much, Prof. Jakovic and Prof. Yu. Yeah, it's make me more curious, of course. Yeah, I hope I can pursue my PhD as soon as possible. So thank you very much for the advice. And yeah, I think I'm the younger on this session. So yeah, thank you very much for the advice. Thank you.
And you definitely should go for PhD. That's always my advice.
Yeah.
Invest. Your life is going to be different. Your responsibilities are going to be different. Your job is going to be different. Yeah, master degree is just a little step, but PhD is really when you grow as a researcher, as a scientist, very different experience. And I never regretted that I actually spent time doing my PhD. Actually, I always wanted to remain a graduate student all my life, but it was not practical.
Thank you very much, Professor Tragovic. Yeah, I will do it as soon as possible, as soon as I can.
Yeah, the sooner
Thank
the
you
better.
very much.
Yes.
Yeah, the sooner the better. Thank you. Thank you.
There is somebody with a hand up there, Muhammad.
Yes. Someone raised a hand. Muhammad Afrizal Amrusti, you can ask for a few minutes because Professor Yu already.
Okay, thank you for the time. I have some question for Prof. Liliana because I want to ask about the topic before you explained before. There is 2 points that I want to ask. The first is how about the implementation of the model that we create, because I also did some research about DDoS attack detection using the CIC datasets, but I'm stuck in how I implement the result of my model. And the second one is about the dataset. Is there any other dataset that we can use as a benchmark, especially in network or attacking or other, because when I read some papers, they are mostly using KAIDA dataset, CIC or NSL KDD. And if I see, especially in CIC dataset, is extracted as a statistical feature. Is there any chance if we can pre-process the raw data into the data that we can manipulate or we can process further? Maybe there is the two questions about the implementation of our attack model and the other data as a benchmark in the network. Thank you.
Okay, let's do one thing at a time. So the first thing is about implementation of the model. What kind of implementation are you talking about? Are you talking about hardware implementation? Because all our models are software models, right? You create a model. Model means parameters, right?
Oh,
So your model are the parameters that you use. Let's say I have the parameters with, let's talk about LSTM. Like I have a model with 4 layers, and the parameters is
Oh, it seems connections problem again from Professor Liliana and Professor Yu. I think they freeze. Okay, they are back.
you need the charger. I can give you a charger. Is it Apple? Oh, no, mine is Apple. You can come here if you want. No, I don't want to take your session. It's your session. You can sit here. We can share. We are in the same room. Okay?
Ah, I see.
We are in the same room.
It's nice.
Just don't come too close because I'm having. Okay. So one thing is, model is the parameters that you get. Your hyperparameters is your model. That means how many layers you have, what are the values of the parameters. So that's your model. Unless you ask about hardware implementation, which is a different topic. We didn't do hardware implementations of these models, which is a really interesting and good idea. Am I answering your question? Am I understanding your question correctly?
Yeah, yes, I got the point
That's
that you
first.
explained.
Yeah. The second
okay.
thing, like KAIDA data is a little bit old. We didn't really look at KAIDA data. We only looked at the graphs because it was interesting. So, and CIC data from Canadian Information Institute for Cybersecurity, it's artificial data. Because you will see for those data, algorithms do very well. But this is in a test bed, right? So this is not a real use. These are not real customers. So for those data sets that come from the synthetic environment, from test beds, they basically created a variety of denial of service attacks in a test bed, in a lab, right? So for those data sets, the performance is different. And my conjecture is it's different because there are no people, right? What makes it very interesting is how people use the internet. Right per route use data sets are real data sets from real networks, right? So KAIDA data set I didn't use. Sorry. There is NSL KDD, which is a bit old. It's already 20 years old, right? What else? That's about it. There are also some other data sets. I forgot the name. There are groups in Australia. They actually have also collections. And there is a group in Japan. But sometimes when we look at data sets, somehow we don't find it very useful. But why are you not happy with Riper route views? To get you started, you can actually use the data from Riper route views and start creating your models. And you can even use CIC dataset to create your models. I'm just giving you a warning that those datasets are synthetic, not real, in a test bed, in a lab. Do I answer your questions?
Okay. If I take the point is the better dataset is the KAIDA dataset because it's the
No, I don't know about KAIDA. I
Oh.
know about ripe and route views. KAIDA
Oh.
is old. I do not know if I collect regularly now. They used to. They also
Oh.
had these experiments called One Day in the Life of Internet. So people would volunteer their own resources to do collection. I didn't follow what they do. But look
Oh.
at the ripe and route views. Ripe and route views
How
to get you started, okay?
how that the spell is
They've been ripe, R-I-I-P.
RIP?
I'll give it to you, okay? Ripe.
Oh, okay. Thank you.
Okay. And so some of my talks are already on the web, and I give talks very often. So if you go on my webpage, on the talks, you can actually find copies of my slides. I always change my slides, but I'm going to show you what it is, okay? Okay, so talks. So if you go on this webpage, you will find some of the talks. Look at the PowerPoint presentations. Go from top to bottom. Don't look at something very old, right? So you can see the presentations. Or you can actually look at the papers also.
Okay, I will bookmark the.
So just to get you started, okay?
Okay.
Because we also give sources of data in our papers, right?
Okay.
But it's all open, okay? To get you started, right? KAIDA, I do not know. I do not know why we didn't look at KAIDA. I didn't really feel they were doing the collection. Ripe and audios, they collect as we speak. They have been doing this for 20 years, right?
Right.
But if you feel comfortable with CIC, start with the CIC. I'm just saying our experience is the data set is artificial. And so the algorithms do very well. And my conjecture is because it's not real. But you can find a variety of denial of the Hulk and I don't know, all sorts of names for denial of service attacks. So that would get you started, okay?
Okay.
And so next question should be for Professor.
Okay, do you have any questions to Professor Yu?
Maybe there is.
All right. Okay, thank you very much for your question.
Thank you
And
very
if
much
there is,
for the answer, Prof. Liliana.
I think it should be the end of our session. And what would I get from Professor Yu is when you do study, you better try to be capable, and then the knowledge will follow the capability. I think that's what I could learn from this session. And do you want to give the last finishing point of your lecture, Professor Yu?
Hey guys, capability is better than knowledge. It can bring you decide what house you will live, what kind of car you will drive. You need to do PhD, guys. Okay.
Yes.
Welcome to Vancouver and Sydney.
And you can
All
apply
right.
to SQ also.
All
And by
right.
the way, you know Professor Hamming, you know Hamming code? He had a
Okay.
saying. Hamming used to say, luck comes to prepare the minds. Okay? Luck will come if your mind is prepared.
Right.
Yeah.
Right. That's
So
a good
you
saying.
have to get prepared. Otherwise, there's no luck.
Right. That's a very good insight word. Thank you very much for Professor Yu and Professor Liliana for the session. It's actually Professor Yu's session, but we got another talk with.
It's lucky to have a senior
Yeah.
correct my
Yeah.
talk.
It's a very, very interesting topic and very mindful discussion. I would like to close this session, and I would like to be a competitor of Professor Liliana on machine learning things. Thank you very much.
Professor Shu is much more successful than I am.
No.
He's more successful than I am.
I'm learning a lot.
Thank you very much. They are both
Thank you.
very capable professor,
Thank
I
you.
believe. Okay, thank you very much for both
Thank
of
you.
professor we have right now. I will give this session back to the MC. Thank you very much.
Okay, thank you to all of the professors, Professor Lilia and Professor Yu, and also thank you to Prof. Mega and Prof. Andy. That was a very insightful session, and I hope that everyone find that as insightful as I do. Okay, and before we conclude, we kindly ask all participants to take a moment to fill out the presence form shared in the Zoom chat. Your feedback is invaluable in helping us to provide a more insightful events like these, truly special. Okay. To close this session, I would like to share a little message with everyone. Let's continue to push the boundaries of knowledge, collaborate, and inspire innovation in the field of communication and networking. Safe journeys on your intellectual pursuits. And until we meet again, have a wonderful day and see you. Bye, everyone.
Thank you.
Thank
Bye-bye.
you.
Thanks.
Thank you, Prof.
Bye.